Welcome to the Deep Dive, where we plunge into complex ideas and really try to unearth the most fascinating insights for you. Today, we're exploring something truly remarkable. It's a breakthrough in the ancient world of numbers, specifically those fundamental building blocks we call primes. Yeah, we're talking about a discovery that's pretty significant. It actually stemmed from a paper that was a runner-up for a major physical science prize. So our mission for you today is this. Let's understand what prime numbers really are, why they've captivated mathematicians for, well, centuries, and how this new breakthrough isn't just adding knowledge. It seems it's actually redefining how we even think about them.
Absolutely. What's really astonishing here is how this research kind of bridges these seemingly separate areas of math. It offers completely new ways, really novel ways, to look at something as old and fundamental as prime numbers. We'll explore how this discovery, it doesn't just fill in a gap, but it potentially opens up entirely new ways of thinking, maybe even practical applications down the line.
Okay, let's unpack this a bit then. Most of us probably remember prime numbers vaguely from school, right? But just to be clear,
Yeah.
what exactly is a prime number?
Right. So a prime number is a whole number, bigger than 1, and the key thing is it can only be evenly divided by 1 and itself. That's it.
Okay. Like the atoms of arithmetic, sort of?
Yeah.
The irreducible bits?
That's a great way to put it. Yeah, the elements that you build all the other numbers from through multiplication.
And the classic examples are 2, 3, 5, 7.
hmm
Keeps going.
Exactly. And for those small numbers, it's pretty simple to check if they're prime. You just, try dividing them. If nothing works neatly, bingo, it's prime.
Right. Seems easy enough at first.
Yeah, but that's where the simplicity ends. Finding small primes, easy. But the challenge just skyrockets. I mean, it mushrooms in difficulty when you get to gigantic numbers. It becomes incredibly impractical, sometimes basically impossible, to just sit there and try factoring them one by one.
Okay, like how big are we talking?
Well, think about the largest known prime number. It's called M825,89933. It's 2 raised to the power of 82,589,933. Then subtract 1. That single number. It's got nearly 25 million digits, 24,862,048 digits long.
Wow. Okay, that's hard to even get your head around.
Ugh.
Imagine trying to factor that.
Exactly. And here's the kicker. Even though that number sounds incredibly vast, it's still tiny compared to the primes that must exist out there.
Because there are infinitely many integers, right? So infinitely many primes, too.
Precisely. So this record holder, it's just a speck in this endless ocean of primes.
Which leads to the big question then, why the obsession? Why do mathematicians care so much about finding these or understanding them?
That's a really important question. Ken Ono, he's one of the mathematicians behind this new discovery. He points out that, yes, we know there are infinitely many primes, but the problem is it's incredibly hard to find any predictable patterns in them or figure out how they're scattered amongst all the other numbers.
So they're fundamental, but messy.
Kind of, yeah. Notoriously erratic. Understanding them isn't just about, tedious factoring. It's about getting to their core nature because so much of number theory rests on them.
And you mentioned applications, so this isn't purely abstract math.
Oh, definitely not purely abstract. Primes are absolutely fundamental to modern cryptography.
Ah, like online security.
Exactly. When you buy something online, it sends a secure email. That security relies heavily on how incredibly difficult it is to factor large numbers that are the product of two massive prime numbers. It's just computationally overwhelming to find those original prime factors without knowing them beforehand. So yeah, understanding primes better, that has huge implications for data security, even for future computing.
Okay, so we have these immense numbers, fundamental importance, practical applications, but they're hard to predict. Mathematicians needed a new angle. And
Okay.
this is where integer partitions come in, which sounds surprisingly simple.
It does sound simple, and that's part of the beauty. Ono himself called integer partitions the stuff of child's play. So basically, an integer partition is just asking, how many ways can you add up positive whole numbers to get a specific target number?
Okay, can you give us an example? Make it concrete.
Sure. Let's take the number 5. How can we get 5 by adding whole numbers? Well, there's 5 itself, then 4 plus 1, then 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and finally 1 plus 1 plus 1 plus 1.
Okay, count. 7 ways.
7 ways exactly. So for the number 5, the number of partitions is 7.
So it's just about counting combinations, essentially.
Pretty much. And this idea, it's actually really old. Goes back to the 18th century, to the Swiss mathematician Leonhard Euler. This classic method of counting mathematicians call it a combinatorial object, specifically the function that tells you how many partitions a number n has, often written Pn. So P5 is 7. And here's the really amazing part. This ancient, seemingly simple idea turns out to be deeply connected to prime numbers in a way nobody expected. It's like finding a hidden key.
Okay, this is where it gets, as you said, mind-blowing. Ono and his colleagues, William Craig and Michael Van Ittersum, they proved something incredible. They showed that prime numbers are the solutions to an infinite set of specific equations involving these partition functions.
That's right. Not just related, but the actual solutions.
So it's not just a new test for primes. It's almost like a new definition.
That's a great way to think about it. It's a fundamental reconceptualization. These specific equations are called Diophantine equations.
Diophantine, okay? Named after Diophantus of Alexandria, right? Looking for whole number solutions.
Exactly. And their finding shows that these partition functions, when put into these specific Diophantine equations, somehow detect the primes. Infinitely many ways, apparently.
Like the partitions hold a secret code for primes.
You could say that. What's profound is that this gives us totally new criteria for saying what a prime number is. It's completely different from the old way. If you can't factor it, it must be prime.
So the old way was about what primes aren't. They aren't easily breakable.
Right. This new way is more about what they are. It's like having a recipe book where only prime numbers can be made following certain recipes using partition ingredients. Their work essentially gives you like infinitely many new definitions for prime, which is, yeah, kind of mind-blowing.
So you could literally take an integer, plug it into one of these special equations.
Any integer 2 or larger, yeah.
And if the equation holds true, then that number has to be prime.
That's what they proved. Rigorously. These equations act like perfect prime detectors. And there isn't just one equation, there are infinitely many of them.
They gave an example equation I saw, but maybe we don't need to dive into the algebra itself.
Probably best not. It's the concept that's key here. These equations are built from partitions, and their only positive integer solutions are the primes. Full stop.
It still feels so unexpected. This simple counting thing connected to the most fundamental numbers. What does this mean for, the bigger picture in math?
Well, connecting this to the broader implications, it really goes beyond just figuring out where primes are scattered. Ono says they're actually nailing all the prime numbers on the nose. It's not just approximating or finding patterns, it's defining them algebraically in a completely new way.
George Andrews, the mathematician who edited the paper, he called it something that's brand new.
Right.
And not something that was anticipated.
Exactly. Which means it's really hard to predict where it might lead. This isn't just taking the next logical step. It feels like opening a whole new door in number theory.
So potential for new discoveries.
Huge potential. It might inspire people to look for similar hidden algebraic structures in other combinatorial functions. It really highlights how interconnected different areas of math can be, sometimes in really surprising ways. And it raises big questions for future research, too. Like, can you use similar ideas for other types of numbers, composite numbers maybe, or other sequences?
Could it even impact those applications you mentioned, like cryptography?
It's possible down the road. If this gives us a fundamentally new way to construct or define primes algebraically, maybe that leads to new algorithms or even new ways to think about the security assumptions cryptography relies on. It's early days, but the potential is definitely there.
Help me grasp this shift again. Why is defining primes by construction through equations so different from defining them by indivisibility?
Think about it like this. For centuries, primes were defined by a negative property, what they don't do. They don't factor easily. This new work gives them a positive identity. They are the solutions to these specific equations. It's like defining human not just as not a chimpanzee, but by describing human DNA. It's a much deeper, more fundamental description. And that kind of shift can unlock totally new ways of thinking and proving things about them.
Okay, that helps. It's a positive definition versus a negative one. But you also mentioned this doesn't suddenly solve everything, right? Like those famous old problems.
Right. It's a massive breakthrough, but it doesn't automatically crack things like the twin prime conjecture. Are there infinitely many prime pairs like 11 and 13?
Or Goldbach's conjecture, can every even number bigger than 2 be written as the sum of 2 primes?
Exactly. Those problems seem to be more about the spacing and additive properties of primes, how they relate to each other. This new discovery is more about the fundamental identity of individual primes. So while it's profound, those other problems have, befuddled mathematicians for generations for a reason. They might need different tools.
Or maybe this new understanding will eventually lead to tools for those problems, too.
That's the hope. Maybe this new perspective, this algebraic definition, will eventually reveal something about their distribution or relationships that we couldn't see before. It's definitely a powerful new lens.
So summing this up for everyone listening, what does this really mean for you? Well, I think it's a pretty powerful reminder that even in fields like number theory, which feels so ancient and established, there are still these fundamental game-changing discoveries waiting. It shows that even things you think you understand, like basic numbers, can have these hidden depths and really surprising connections.
Absolutely. And it highlights how these abstract ideas, like counting partitions, can suddenly become the key to unlocking really deep insights somewhere else entirely. It just shows the amazing richness and interconnectedness of mathematics.
So next time you're banking online, using that cryptography, or maybe just thinking about numbers, remember the primes. And maybe think about them not just as indivisible, but as these elegant solutions popping out of infinite equations based on simple sums. It's quite a thought. Makes you wonder, doesn't it?
Yeah.
What other hidden connections are out there waiting in fields we thought were completely mapped out? Thanks for joining us in this deep dive into the strange and wonderful world of prime numbers. We hope you found some fascinating nuggets today.